The good news about capacitors is there is basically only one graph that you need to do. Okay? You need to draw a graph of the amount of charge separated. So the amount of charge separated against the voltage that you produce. Okay? Let's think about that graph. Here we are with the thing uncharged. So here's the capacitor minding its own business. We decide to separate 1 electron's worth of charge. So I'm sorry this diagram's got a bit scribbly, so forget about all these electrons. Let's imagine we turn the circuit on and we take 1 electron off of here and we push 1 electron onto there. So you've basically separated, well, 1 E's worth. Yeah? If E is the electronic charge, the charge on the capacitor, if we separate 1 electron's worth, okay? How much voltage will we get? Well, we'll come to this in just a moment. Let's make life easy, let's suppose that if you separate 1 electron's worth, it produces a voltage of 1 volt. Now, you'll see pretty soon that's quite an unrealistic capacitor, but let's keep things simple. I'm going to separate 1 electron. That means taking it off of this side and shunting it around to that side. And that's going to create a tiny voltage. Why? Because the insulator in the middle that is like a little spring has now got to work. It's got to hold that little vacancy for electron, the plus and the minus. It's got to hold those apart. And let's suppose that produces an amount of energy equivalent to 1 volt. How much voltage would I have if I separated 2 electrons? 3 electrons? Just go up, wouldn't it? So basically, can I convince you, the good news is this is just a straight line. Doesn't look like the easiest graph in the world, the charge separated against the voltage on a capacitor, but it's desperately easy. All electrons are the same. You can put that next to the line if you like. Very importantly, all electrons are the same. If you separate 1 electron's worth, or 2 electrons worth, or 3 electrons worth, they're all the same. So if you take an electron off one side, put it on that side, and that produces a potential energy equivalent to 1 volt, if you do it with another electron, it'll be 2 volts. Do it with another electron, it'll be 3 volts, and so on. This graph has to be a perfect straight line. Unless you get a particularly big electron, and moving that makes extra voltage, and the graph goes up with a bit of a bump. That just obviously doesn't make sense. Why is this graph a straight line? Couldn't be easier, because all electrons are the same. Okay? Now, let's call that capacitor A, and we're going to introduce another capacitor, called capacitor B. And the question I'm going to ask you is, which is the better capacitor? You're thinking, I've lived my life without using a capacitor ever, so I don't really care. Which of the two is the better capacitor? Because? Well, it stores what, sorry? Oh, hang on a minute, stores? Separate, good, that's what I thought you said. Well, you can separate the same amount of charge on either. If you want to separate 10 electrons worth, I can do it with capacitor B and I can do it with capacitor A.
It doesn't make the battery go as flat with the same amount of charge, so.
Yeah, because it doesn't develop as much voltage. Look at capacitor B. Let's suppose the job to be done is to shift 10 electrons worth of charge. Capacitor B will do it with only 5 volts. Capacitor A would build up 10 volts. Why is building up only 5 volts compared to 10 a good thing? Imagine it's a 10 volt battery in the circuit. What advantage does capacitor B have over capacitor A?
It's too involved in the circuit.
Yeah. What will capacitor A have to do at this point? Stop. If you've got a circuit, let's pick better numbers really. If your circuit's a 10 volt battery, what's capacitor A going to be at this point? It's going to be fully charged, isn't it? Fully charged is a bad word, fully voltaged. Can you see capacitor A would have to stop at this point because it's reached 10 volts. Capacitor A can separate 10 electrons worth, no problem. But in so doing, it develops 10 volts. Now, if that's the voltage of your battery, that means the process is over and you can't separate any more charge, you can't store any more energy. Capacitor B, however, be clear about this. This is a difficult graph because the two things are just both very abstract things. Charge and voltage are not things you see walking down the street every day, so you need to concentrate on this. Capacitor B can separate 10 electrons worth of charge, but when it does it, it only generates 5 volts. It's made differently or something. It only generates 5 volts, which means in the circuit it can keep going. In fact, capacitor B can keep on going. Sounds like an advert, doesn't it? To there. Yeah? So we would say that we like capacitor B. Capacitor B is a good capacitor, and capacitor A is a bad capacitor. That's what that really means. Can you see the advantages of capacitor B? Yeah? It can separate any amount of charge compared to A, but it can do it with less voltage. Generally, you want to separate charge because if you separate charge, you're storing energy. The downside of that is that you generate a voltage. Now, the voltage across the capacitor isn't itself a problem, but it is going to oppose the battery. If you're thinking, why is this the bad axis? Is it because it will oppose the battery, and ultimately that will stop the thing from charging. So this has an advantage capacitor at B because for a given amount of charge it will produce less voltage. Okay? And it's the voltage which eventually stops the thing from charging. Okay? Right, well let's make up a number. You don't buy capacitors by their goodness or badness. Our technician doesn't phone up and say, can we have half a pound of bad capacitors? We need to make up a number. Have a look at the graph. Line B is for a good capacitor, and line A is for a bad capacitor. Can you think of anything about line B that's bigger than for line A? Gradient. The gradient of this line is going to work well because you can see for capacitor A you'll get a fairly small number, in fact 1. And for capacitor B, you'll get a bigger number. Yeah? So can I convince you that the gradient of these lines is going to be linked to something useful? If I tell you I've got a capacitor and it gives me a really steep line, it's got a gradient of 85 million or something, you go, blimey, that's useful. That number that you've told me tells me it's going to be a really effective capacitor because it will separate loads of charge and hardly generate any voltage. If I tell you I've got another capacitor that's got a gradient of 0.1, it's like that. That's not necessarily a very useful capacitor in most cases because you'll only separate a little bit of charge and it's immediately got like 10 volts on it and the whole thing stops charging. Okay? So the way to think about this next bit is to think about the gradient of that line. You might think, why didn't you put voltage up the side because it looks nicer? If you draw it this way round, charge against voltage, then the gradient is a very useful number because it will effectively give you a measure of how effective the capacitor is capaciting, whatever they do, I don't know. B is the nice capacitor and A is the nasty one. That's all you need to know. Okay? What sum would we do to calculate the gradient of these lines? Charge over voltage. Alright. A very useful thing to work out is going to be charge over voltage. Alright? Charge over voltage, the other piece of good news, it's the same all the way along, isn't it? These are nice straight lines, and they have to be, remember, all these lines have to be straight lines. So the good news about the gradient, of course, is the same number all the way along. Okay, so I can just have one number for A and one number for B. The important thing is the number for B will be bigger, indicating it's one that can separate a lot of charge without producing much voltage. Now, no prizes for guessing. Charge over voltage for a capacitor is called its capacitance. I wouldn't write this in the exam, but capacitance kind of tells you how good a capacitor it is. I really wouldn't write that in the exam because it's a load of twaddle. But it does in a way, because a big capacitance means you can separate a lot of charge without generating much voltage. That's not an easy sentence, but you might want to write that one down. A high capacitance means you can separate a lot of charge without producing too much voltage, which is a good thing apparently. Okay? High capacitance separates a lot of charge without much voltage. Low capacitance, you separate a small amount of charge and you've already got a massive great voltage. Okay? Right, let's put the units in. This is going to hurt. Units of charge. Coulomb. Very good. Well mumbled. Voltage.
Volts.
Well done. Capacitance, I'm afraid, has a new unit. The unit of capacitance, the Coulomb per volt if you like, you'll be glad to know you don't have to go around saying Coulomb per volt all the time, is the farad. Okay, named after Michael Faraday. The capacitance is measured in farads. Right. And a farad is, pretty obviously, Coulomb per volt. Yep. Say again? Capital F, yep.
When it comes to the exams, will there be a different data sheet to the one we've just had?
Oh yeah. Oh yeah. No, the A-level one's got all these horrible stuff on. You have got this equation, I think, on your data sheet, but it's a pretty straightforward one to learn. Based on the gradient of this graph, all right, capacitance is charge divided by voltage. Okay. And it has a unit, the farad, which is coulombs per volt. It's a tricky idea, but the way to hold on to it is it tells you how good a capacitor is. How much charge can you shift for how little voltage? All right. We have a slight problem with the farad. The farad is what we call a derived unit in physics. That means it doesn't really decide how big 1 farad is. 1 farad has to be 1 coulomb per volt. And 1 volt is 1 joule per coulomb. And you can kind of trace that path back, but the farad basically is very big. I think somebody once told me this is true. If you took the earth and hollowed it out, and you painted the inside with sort of aluminium, and you put a pin in the middle, can you see you've got 2 conductors separated by an insulator? Because obviously the great big hollow thing would be full of air. That would have a capacitance of just under 1 farad. All right, so the capacitance of the Earth is probably not much more than 1 farad if it were made into a capacitor. So we need to get used to, I suggest you jot these down because you're going to use them all the time. The millifarad, which is pretty obviously 1,000th of a farad, you know that from your millimeters. The next one down is the microfarad, which of course is 1,000,000th of a farad, or 10 to the minus 6. Okay. The nanofarad, which is 1 over lots of things, is 10 to the minus 9. Okay. And the next one? It's the picofarad, isn't it? 10 to the minus 12. Is 1 over 1 with lots and lots of zeros, is 10 to the minus 12 of a farad. All right. You do regularly get exam questions right down here. Okay. In olden times, a millifarad capacitor, you could really hurt somebody with it if you hit them with it. All right, a millifarad. So if you're doing calculations, this is a good point for the exam. If you're doing calculations and you get the answer of 6 farads, you've made a mistake. Unless it's asking about the capacitance of the solar system or something, you've got it wrong. All right. Anything you can fit in a circuit on Earth, you're going to be down in the millis and probably the microfarads. Okay. The farad is unfortunately a massive unit. It's way too big, and every calculation you do in A-level to do with farads and capacitors is going to be in the milli or more like the micro or even the nanofarad. And I have seen questions about what picofarads. So your prefixes milli, micro, nano, pico. You need to remember them. You are going to be using them every single time we do something on capacitance. Okay. Now, I have some even better news, which is we can finish the whole topic by 4:45, because that graph really does everything you need to know about capacitors. So I will just take that off. I'm running out of room. Let's just remind ourselves, we've got charge up here against voltage. Okay. Charge against voltage looks like that. If you take the gradient then you get the capacitance. Now here's some really bad news. Capacitance has the letter C. Why is that a bit of a potential nightmare? It's the Coulomb. Can we just write this down once and get it right for the rest of our lives? Everything in physics, every law in physics can be written in terms of quantities and units. In terms of quantities, it's this. Here's the formula for capacitance. Capacitance equals charge Q, do you remember that? Divided by voltage. Units is the farad is a coulomb per volt. Alright? You need to be very careful. A number with a C after it is obviously telling you the charge in coulombs. But the letter C in an equation is the quantity capacitance. These are the quantities here. Capacitance, charge, voltage. Here are the units, farads, coulombs, volts. The volt is even more confusing because it has the same letter. The quantity voltage is V and the volt is a V. Alright? But here's the potential confusion. The quantity capacitance and the unit, the coulomb, both have the letter C, so you need to be very careful. Okay? So capacitance here is Q over V. Now, we've measured the gradient of this line. We decided this is a useful line to draw for capacitors, the graph of capacitance against voltage. We've measured the gradient, and that's a useful number. The gradient is called the capacitance, and it tells you how good a capacitor is. What else can you measure about graphs? Or lines on graphs? You can measure the gradient or the area. You can do the area. Let's imagine we charged our capacitor up to this point, and we then said we're interested in the area. Okay? So one thing that you can get from most graphs is the gradient. In this graph, that's called the capacitance. The other thing you can get from most graphs is the area. So number 2 is the area. Let's just see what that tells us. It may not tell us anything useful, but let's see how we go. What units will the area have? What units will, oh, it's half the base times height because it's a triangle, we'll get to that in a minute. But what units would the area have? How would you work out the units of the area? What would you do with these two units to get the units of the area? You times them together. To get the units of the gradient, you divide them. The gradient has units of coulombs per volt, what we call the farad. But the the area will have units of coulombs times volts. What might a coulomb times a volt be?
Coulomb volt.
Very good. The volt, you know though, a way of writing the volt, don't you? The volt, we'll read it off now. What's a volt? It's a joule per coulomb. Yep. So what's that going to be? If a volt is actually a joule per coulomb, it's joules. What do you think the area of this graph represents? The energy stored. Energy stored? There it is, that's right. The energy stored. The area under this graph will tell you the amount of energy stored in the capacitor. And yes, you are allowed to use the S word, because they do store energy. Okay? So the area under the graph is, again, a useful quantity. It tells you the amount of energy stored. The gradient tells you the capacitance. The area tells you the energy stored. Okay? And obviously a bigger capacitor at the same voltage is going to store more energy and so on. Okay? Let's finish off by seeing if we can do an equation for the energy. As I said, you take the gradient, that gives you C equals Q over V, which is the definition of capacitance. You take the area, and that will give you a formula for the energy. Anyone who's good at half the base times the height like to tell me an equation for the energy? The area of that. Drop the other one off actually. Well, let's do it properly. Let's do the letters. Charge is Q in coulombs. And voltage, well, voltage is easy. Q is voltage in volts. What would be an equation for the energy stored? That's it, QV. So there we go. Everything you need to know about capacitors is on this graph. Q against V is a straight line, because all electrons are the same. The steepness of the line, the gradient, Q over V, is a new quantity to you. It's called the capacitance, and it tells you how good a capacitor is. The area under the graph, which of course will be half QV, half the base times the height, is going to give you the amount of energy stored. Okay? The only thing is, just to finish off, that isn't very helpful. Think about it. You get a capacitor, it says on the side 85 millifarads. You shove it in a 12-volt circuit and someone says how much energy is it storing. You go, well, I don't know because I don't know how much charge is separated. It's not a very good way of doing it. This is absolutely correct. This is from the graph, this is the definition of the energy stored in the capacitor. The problem is the Q makes it, in practical terms, a very difficult equation to use. Can anyone see a way we could get rid of the Q in there? Could we use this other equation? What's Q then? From this?
V times
CV, isn't it? Yep. If I put that in there, anyone good at maths and substituting and stuff?
Q equals half CV squared.
Half CV squared. Alright. Can I introduce you to the alternative version of this equation? Half QV is brilliant because it drops straight off the graph. Half times base times height. If you've been asleep for the whole lesson, if you remember this graph, remember why it's a straight line. If you know the gradient is C equals Q over V, which tells you about capacitance, and you know the area is a half QV, is the energy stored, that's fine. But I can promise you that half QV is a very difficult equation to use because you generally don't know Q. Much better is to use this version, a half CV squared. 85 millifarad capacitor, 12-volt circuit, you're there. You know the capacitance, it's written on the capacitor. You know the voltage because it was you that got the battery. You can work out the energy stored. Think about it in practical terms. You've got the equipment on the desk in front of you. You don't normally know Q. And you could say, well, I could work it out using this and then go into that equation. Well, just save yourself a step. All right? So if you like, there are two versions of the energy equation. I can promise you this is the one you're going to be using. All right? A half CV squared is much easier to use in practice. Okay?